Performance Monitor allows you to trace the execution of your code. It's a powerful tool that allows you to troubleshoot real-time issues, understand the overall CPU loading, and tune your system. In this tutorial, I'll trace the execution of some File Manager app commands to illustrate the Performance Monitor. The Performance Monitor is a combination of CFE executive service features, applications using the service, and a ground tool that processes and displays the data. Applications define performance identifiers and make calls to the CFE executive service when they enter and exit execution. This is commonly performed when an app pens for a software bus message or for a synchronization mechanism like a semaphore. An operator sends commands to executive service to configure what data should be collected, when the data should start and stop, and the data file to be used. After data collection is complete, the operator transfers the data file to the ground. The last step is to start the cFS Performance Monitor tool, or CPM, to display and analyze the data. We're going to trace the execution of two apps during this demo. File Manager pens indefinitely for a file service command. It uses a child task to perform most of its file services, and the two commands we'll be using are both executed by the child task. Memory Dwell pens on a 1 Hz packet from the Scheduler app. Memory Dwell's functions are not relevant to this demo. I picked Memory Dwell so a clean 1 Hz signal could be captured. Note that both of these apps process send housekeeping requests, but I've disabled the request so the execution trace is cleaner. The data collection scenario is pretty simple. We'll start the data collection, wait 4 seconds, send FM a command to send a directory listing in telemetry, wait 4 seconds, send FM a command to write the directory to a file, wait 4 seconds, send FM a command to send a directory in telemetry again, wait 4 seconds, and then stop the data collection. The send directory command in telemetry only sends 20 file entries in a packet, so it should execute faster than writing the entire directory to a file. For each command, we should see FM's execution go active, immediately followed by the child task execution. Note that the Memory Dwell 1 Hz signal is asynchronous to the command being received by File Manager. Here are the items that must be configured for collecting data. Applications define performance IDs that must be unique within a platform. The current convention is to define performance IDs in an app's mission include directory using the app_perfid.h naming convention. A CFE executive service command sets the filter mask, and that defines which performance IDs will be logged. An executive service command sets the trigger mask that defines which performance IDs are used to start the data collection. Data collection can also start just with the reception of the command, so you don't have to have a trigger mask. A mask is an array of 32-bit words where each bit corresponds to a performance ID. So understanding how to set masks does require knowledge of the binary and hexadecimal numbering systems. Here are the performance IDs that we'll be using. So here's how Memory Dwell's app, ID decimal 26, is converted into a bit mask ID. Each hexadecimal digit represents 4 bits. The first 6 digits gets us the bit 23, and this is from 6 times 4 minus 1 since we start counting from 0. Therefore, to get to bit 26, we need to go 3 more bits into the next nibble, which is the hexadecimal number 4. File Manager's app performance ID is 39, so we need to go into the second 32-bit mask word that starts at bit ID 32. The second nibble in this word starts at bit ID 36. So to get to the 39, we need to set the last bit in the second nibble, which is a hexadecimal 8. Finally, for File Manager's child task of an ID 44, we know that the third nibble in the second mask word gets us to bit ID 43. So setting the first bit of the next nibble is ID 44. Next, we'll go into OpenSatKit to put this scenario into action. I'm now in OpenSatKit. I have a terminal window open with the cFS is already running, and I have the Cosmos script runner open. I'm going to run everything from a Ruby script for this demo. So let's open the file. It's called perfmon_demo, and I'm going to start it. The first thing it's going to do is do some setups, and then it's going to stop at a wait statement. So the first thing it did was bring up the Performance Monitor screen, and here we see a bunch of buttons for commands that we're not going to use because we have everything driven from the script. We see the current status, it's idle. Start mode means it's going to start collecting at the trigger point, and we have a trigger count of 0. Here are our filter masks. Here are the trigger masks, the 4-bit mask words. And then we have some other statistics or stats here that start count and how many data points that it's collected. Then at the bottom we have some convenience mechanisms for transferring files. Again, we're not going to use those. And the other thing it did in the startup was enable debug events for File Manager, because that makes it easy. You can watch the directory commands get echoed here. Then we also disabled the scheduler table entry requesting housekeeping requests to the 2 apps that we're using. So now I'm going to hit go, and it's going to set up the mask. So it's issuing 4 commands. It issues 1 for each mask in the array. So here we see the mask that we've identified for File Manager and Memory Dwell. Now we're going to set the trigger mask up. And again, that's just going to be the 1-bit. Now we're ready to go, and it's going to go through the scenario. So the first thing it's going to do is start the analyzer, or the capture. So it's been triggered, it's started, and it's already capturing. We see that the command is being write the directory to a packet, write it to a file, then write it to a packet again. We're going to do a stop. So we're going to see it go back to idle and the number of points it's collected. And now it's at a wait statement, waiting for to transfer the file and then start the tool. Another thing that went by quickly, you may have noticed. So here's just some error checking. I like to put that in my script so that I know it did some sanity checks to make sure everything worked before we got to this wait point. So I'm going to hit go again, and we'll see that TFTP successfully transferred a file. It's now waiting at cleanup, so we don't have to worry about that. And it's launched the tool. So I'm going to go into log and do a read log. The name of the file was perfmondemo. I'm going to select that. It says we have 3 IDs in the log file, which is what we expect. And now we see a display. And before we analyze the display, I want to bring up that here are the performance IDs, and they're written in hex. But you can actually configure the tool to use symbols for IDs. So I already have it pre-configured with a perfmondemo IDs. We're going to load these. And the nice thing is now we see it's Memory Dwell app, File Manager app, and the child task. So here's the Memory Dwell 1 Hz signal, nice and clean. Then we see the 3 commands for FM. We have write directory to a packet, to a file, to a packet, and then the child task performing the action. And note this top line is the total CPU activity for all of the IDs we traced. It's not, since we're not doing the whole CPU, this is not going to give us the information in terms of CPU loading. And now we can analyze the data. So why don't we start with the write file to packet. And what I'm doing is holding my left mouse down so I can zoom in. And then I'm going to use a feature of where you can mark deltas. So if you notice at the top where it says start, end, and delta, I'll go back down here, and we can see that this took nearly 4/100ths of a second. So that was the directory writing to a file. I'm going to use auto range to quickly get back out. Now we can go over here to the last one, which was writing to a packet. And if I mark that, it looks like it might not have stuck. So let's go backwards. We'll just get a negative number, but that's fine. So and this looks like it took even less than 1/100th of a second in order to write the telemetry packet. So as we expected, it took much longer to write the full directory to a file. I'm not going to go through all the features of a CPM, but I would like to point out 2 other things. There's the main tab. So there's other analysis you can do. This one is trying to thread together the performance IDs into an execution stream. And this doesn't make a lot of sense since Memory Dwell is not related to the file management activities, but I just want to make you aware of that. And then there's also statistics, and you have different ways of viewing them. And this can be very useful when you want to look at the overall CPU loading and you use all your performance monitors. Again, in this case, it's not going to be very meaningful since we're only tracing 3 IDs. This was a trivial example to illustrate the mechanics of how to use the performance monitor. In reality, it's more challenging, so here are some guidelines. When possible, design a synchronous system. This will allow you to strategically manage CPU loading. It will also help with the next guideline, which is to create repeatable tests. Once you know what you want to measure, you must be able to measure it under controlled scenarios multiple times. There are limits on how much data you can store, so you can't simply collect everything over long periods of time. You can also get creative on automating when the start data collection command is sent, based on a particular state or event. When possible, divide and conquer the problem space. This is more feasible the more synchronous your system is. For example, if you don't need to load all of the apps to troubleshoot a particular issue, then it may make sense to work with a reduced system. However, be careful because false assumptions about root causes of problems can blind you from seeing the real problem. Finally, I'd like to mention a few of the executive service configuration parameters that you should be aware of as you expand your use of the tool. You can define the maximum number of performance IDs, the max size of the data buffer, and the last two let you control the execution of executive services child task that does the actual data collection. You can tune the number of milliseconds between executions, and you can also define the number of entries that are captured during each execution. Remember, the performance monitor is actually part of the system being measured. This concludes the Performance Monitor tutorial. Thanks for tuning in.